Who is your team member? You want to share it on YouTube or?
Good morning, everyone. My name is Effiong Masbasi, and with me, my team member is Trumpet, Walkland Bronze Trumpet. His name is very difficult. Thank you for having us today. Today we'll be talking about application of fluidization in food processing. I know my own part of the job here is in this content I will be handling from 1 to 3. I will first of all talk about what fluidization is. We have just been hearing fluidization, fluidized bed. So I will explain the principles of fluidization and what fluidization is. Then I will move on to giving a brief introduction, history of its applications, and then I will explain the basic types of fluidization, that is aggregative fluidization and particulate. Then I will look at general classifications and third group. Then I will just give a bit explanation on minimum fluidization velocity and give also a bit explanation about the advantage of heat and mass transfer in fluidization. Then I'm also expecting that at the end of my presentation, your knowledge about basic principles of fluidization should be more enhanced. Thank you. So, actually, what is fluidization? Before we can answer this question, I would like to ask do we think that the fluidization process is similar to liquefaction? No. Okay, someone said no. But before you can be able to answer this question, what is actually fluidization? Okay, and what is liquefaction? Liquefaction, you know, you are condensing the gas, okay, to what? To liquid. So liquid will be formed. So that means that in fluidization, there will be no liquid. So you are extremely correct. So what is fluidization? Fluidization can actually be looked at a process whereby static fine solid particles, static gets the word, static fine solid particles are being converted into a dynamic fluid-like state particle. Fluid-like, not fluid, fluid-like state particles. If you look at this diagram very well, how does this mechanisms happen? From this diagram, first of all, if I have, for example, there was no fluidization happening here, then I just have my solid particles here, and then I pass my fluid. I pass my fluid, which is gas. It can be gas and it can be liquid, okay? From here, using the help of a distributor, which were taught by professor, maybe a perforated plate or something. So if I pass the gas there, what happens to the solid, the fine solid? It will start moving, right? So it will move in a kind of fluid-like nature. Now, if it moves in a fluid-like, if it moves like this, and moves in a fluid-like nature, that means fluidization has taken place, right? But actually, if these particles moves upward, you are expecting a force. It will be trying to balance. And that means we can expect a different kind of force, maybe the buoyant force, right? We can also have the drag force, trying to drag it down, and we can also have what? Gravitational force. So I want to ask a question. If we add the sum of the drag force, the force trying to drag it down, and the force of the particles trying to float, if that force is less than the gravitational force, will these particles go up? No, it will not go up, right? So, but if the sum of the buoyant force and the drag force is maybe approximately equals to the gravitational force, that means the particles will do what? Float. So this is just the basic principles of fluidization. Like the particles, first of all, the fine particles, first of all, has to be fluidized by a fluid, which is either a gas or solid. So that means that you can have a gas solid system, or what, a liquid solid fluidization, or you have what, a gas liquid solid fluidization. Okay, so then we'll move briefly to the history of fluidization. I know we know this guy Winkler classifier. It was a German researcher that actually first of all designed a Winkler classifier, which was used for actually for a coal plant. Okay, now for the coal plant, for this kind of reaction that leads to formation of synthesis gas, according to him, that this synthesis gas can be converted from Fischer-Tropsch process to liquid oil. Okay, so Winkler was able to first of all design this gasifier in the early 1930s, which leads to other commercial design of other fluidized bed. And from there, from his own design of this kind of fluidized kind of commercial gasifier, it led to the US researchers also designing another, the first world FCC gasifier at Louisiana Art and Science Museum. So then, since then, the fluidization design and application has been growing worldwide, especially also even in like maybe metallurgical industry, energy industry, petrochemical industry, oil and gas. And that was actually that US researchers, the group of US researchers that designed this FCC was in 1940s, the early 1940s. So like currently also in China, we have a combustion fluidized combustor, which has a capacity of about 650 megawatts production. Now, moving into the types of fluidization, I mentioned that I will explain these types of fluidization based on the solid properties, okay, the kind of fine solid. So you have particulate fluidization. What if we think of particulate, from the word particulate, we might think of little particles. And if we talk about aggregative, we might think of accumulations of particles. But what actually is particulate fluidization? If you look at this diagram, we have understood the fluidization process. If you look at this diagram, these are the solid particles. When fluidization happens, if the solid particles are uniformly distributed around, we call it what? Particulate fluidization. But if the solid particles are non-uniformly distributed, we call it what? Aggregative fluidization. And they are a kind of condition that requires some particles to either be undergoing particulate fluidization or aggregative fluidization. One of such conditions is that probably the minimum fluidization velocity must be less than the gas velocity, which is in turn less than the minimum bubbling fluidization velocity. And also in aggregative fluidization, of course, aggregative, so the gas velocity must be greater than the minimum fluidization velocity. Now, in terms of classification, we talked about Gidal classification, and it's not actually new to us. we know Professor Jidals actually classified powders particles into 4 different groups, okay? Group A, B, C, and D, okay? And then it classified these particles based on their density and the particle diameter. Most of us we have been doing some calculation about grace diagrams and others. So it's just like to look for the particle locations in the fluidization regime. So looking at group A, B, C, D, why do we need these particles? Why do we need particle classifications? Because we need to understand how these particles behave when they are fluidized. So what are actually the properties of these particles? For particles, in group A particles, they have a size of 30 to 100 micrometer. An example is FCC catalyst. Now you can see group B particles 100 to 1000 micrometer. Example is sand. And then group C is cohesive. Okay, is a kind of like cohesive particles, and from 0 to 30 micrometer. An example is flour. And then you have particle D. You could see that is packed. Okay, an example is just is lead and zinc, and it has lead and copper. It has size greater than 1000 micrometer. Now, in these particles, which of them, you might want to ask, which of them undergoes particulate fluidization and which can undergoes aggregative fluidization? So, in a gas solid system, group A particles actually undergoes particulate fluidization, while B and D undergoes aggregative fluidization. But C is actually very, very difficult to be fluidized because of what? They have the same size, okay? They have the same nature, and they have a very strong cohesive force between them. Now for fluid number actually take into consideration the centripetal force and the gravitational force. And then for particles to actually undergo particulate fluidization, the fluid number must be less than 1. Okay, if the fluid number is greater than 1, then it will undergo aggregative fluidization. Now, in terms of aseptic processing of particulate food, and aseptic, you're actually using this to prevent your food from spoiling. For most of us, we might just heat up our food from spoiling, okay? So, but we need to understand the heat and mass transfer. So the heat and mass transfer can help you to have, in the fluidized bed, can help you to have a very high yield if you have the knowledge of how the heat and mass transfer takes place. You can have, like from here, like 3% from step 1 to step 3, 3% of the yeast concentration was gotten. Now, my next point is to explain here the minimum, how the minimum fluidization velocity is being applied in food processing industry. Just a little bit concept, and my colleague Topet will actually deal on the applications very well. Now, what is actually minimum fluidization velocity? From this diagram, you could see UMF. So it's actually showing a relationship between the pressure drop and the gas superficial velocity. The pressure drop, the relationship between the pressure drop and the gas superficial velocity. So this intersection you can use the minimum can give you the minimum fluidized velocity. Now, but in terms this in food processing industry, for them to actually determine the minimum fluidized velocity, in spherical, like foods that are round, spherical, okay, is very easy. But when the shape of maybe the food is slightly different, maybe cubic, like maybe in French fries, like this, okay, this is not spherical. It's very difficult. So how do they do this? They actually apply the Egan equation, which we learn. They actually apply the Egan equation, and then from this Egan equation, it can be solved and adjusted. This particular diameter, this particular, it's called the ferricity of of the particle size. So this can be solved and adjusted to actually determine the minimum fluidization velocity. So I think that will be all my part. So I invite my friend here to come and complete the remaining. Thank you very much.
So my part is to talk about the specific application of fluidization. There are three applications that I want to talk that are freezing and cooling, spray drying, and agglomeration and fluidization. Let's see the freezing and cooling first. The first application of freezing using fluidization was in 1950 in England. The particle also freeze very quickly. The example P will freeze in 5 minutes, and the fish finger will freeze in 15 minutes using air at -3 Celsius degree. Also, prawns will freeze in 15 minutes using air at -37 Celsius degree. The product that is produced is free flowing and undamaged, since the particles are individually suspended in the air stream. So air cushioning will help prevent aggregation of the food particles. And there are two main ways in which food can be frozen using fluidization. One method is to directly suspend the particles in the cold gas stream. This is known as the direct fluidization technique, or DFT. And the other method is to use a two-component fluidization. This involves immersing of the food to be frozen. This technique known as the freezer immersion technique, or FIT. This technique is better for prepared foods because there is less risk of contamination of the food by inner support material. And the DFT method is better for small particles food. And there are 3 types of fluidized freezer in common use. The first one is gravitational flow. The bed is slow so that the food material flow through freezer under